You know, when you see a robot move with such perfect, fluid precision, have you ever wondered what's going on under the hood? It turns out there's this hidden, almost poetic language that describes it all, a really elegant way of looking at motion and force. And today, we're going to dive into that unified language, screw theory.
So, what's the big problem we're even trying to solve here? Well, the main challenge with robots is this. Trying to describe how something moves in 3D space is surprisingly tricky.
See, the old school way of doing this treats rotation and translation like two totally separate things. You've got these rotation matrices for turning, and then you've got these translation vectors for moving from point A to B. For a simple robot, that's maybe fine. But when you've got a complex arm with 6 or 7 joints, oh man, trying to keep track of all those separate parts becomes a real headache. It's clunky, and it's just not intuitive at all. But that begs the question, right? What if there was a better way? What if we could use a single mathematical object that just combines them all? And it turns out there is. This leads us to this beautiful idea of a unifying screw motion. It's a really elegant insight that comes from a brilliant observation called Shaw's theorem. And this is the core aha moment. Shaw's theorem basically tells us that any movement of a rigid body, no matter how complicated it looks, can be boiled down to a simple rotation around an axis and a slide along that very same axis. Just think about turning a screwdriver. You're rotating it and pushing it forward at the same time. That's a screw motion. Every single possible movement can be simplified down to that one single intuitive action. Okay, so to capture this idea with math, we use something called a screw. Now, don't let the name intimidate you. A screw is just a 6-dimensional vector. And what it does is it cleverly packages a 3D vector for rotation and another 3D vector for translation into one single neat entity. No more juggling different pieces of math. It's all in one place. Now, this is where this new language really starts to open up. Screws come in 2 main flavors. The first is called a twist, and that describes the velocity of a body, like how it's moving at this very instant. The second is called a wrench, and that describes all the forces and torques acting on that body. You can really think of them as 2 sides of the same coin. One is for motion, and the other is for forces. So now that we have those core ideas down, let's get a little more familiar with twists and wrenches. This is basically the vocabulary of our new language. What makes the screw concept so versatile is a property called pitch. Think of it like a knob you can turn. If the pitch is 0, you get pure rotation, like a spinning top. If you crank the pitch up to infinity, you get pure translation, just like a box sliding across a table. And for everything in between, you get that general corkscrew motion. And the exact same logic applies to the forces and moments described by a wrench. So how does this actually help us with robots? Well, it's perfect. The most fundamental joints are described so beautifully by this. A revolute joint, one that just rotates, that's just a simple twist with 0 pitch. A prismatic joint, one that just slides back and forth, that's a twist with infinite pitch. It's simple, it's geometric, and it just makes sense. Okay, so how do motion and force, our twists and wrenches, actually interact? The key is something called the reciprocal product, which is really just a fancy way of calculating the work being done. This leads to this super powerful concept of reciprocity. If this product is 0, it means a force, the wrench, does no work on the body's motion, the twist. Imagine pushing straight down on a block that's sliding sideways. Your force is totally perpendicular to its motion, so you're not doing any work to speed it up or slow it down. It's a really elegant way to define the relationship between how something is free to move and the constraints that are acting on it. All right. Theory time is over. We've got the concepts down. Let's actually start analyzing some robot motion and put this powerful language to work. So here's the #1 application, what we call forward velocity kinematics. And the goal is pretty simple. If we know how fast each of the robot's joints are moving, how fast is the tip, the end effector, moving? Screw theory gives us the answer with something called the geometric Jacobian. And this Jacobian isn't some abstract math thing. It's literally a matrix that's built directly from the twist of each joint in the robot arm. And building it is incredibly logical. Check this out. Step 1, you figure out the twist that represents each joint's motion. Step 2, you use some simple coordinate transformations to make sure you're describing all those twists from the same point of view, usually the robot's base. And then step 3, the final motion of the end effector is just a simple combination of all those individual twists. It's a direct geometric process. Let's look at a quick example to make this really concrete. So here we've got a simple planar 3R robot. That just means it has 3 revolute joints that all rotate around the same axis. We define a twist for each of those 3 joints, pop them into our base frame, and then we just stack them side by side to build our 3x3 Jacobian. It is literally that straightforward. But here's where you really see the power of this whole approach. We can take the exact same logic and apply it to a much more complex robot, like a 6-degree of freedom industrial arm you'd see in a factory. The principle is identical. We get a 6x6 Jacobian by just assembling the 6 joint twists. This method just naturally handles any combination of rotating or sliding joints without all the headaches of other methods. It just works. It scales.
So, we've seen how to get velocity from joint speeds. That's awesome. But screw theory has one more incredible, absolutely elegant trick up its sleeve. Let's look at the ultimate payoff, what's known as the kinematics-statics duality.
And this is the big reveal, the mic drop moment. On the left, you've got kinematics. The joint speeds go through our Jacobian, J, and that gives us the end effector's velocity or twist. On the right, you've got statics. Say an external force, a wrench, is applied to the end effector. How much torque do we need at each motor to fight against that force? Well, the answer is given by the Jacobian transpose. The exact same matrix that connects velocities also connects forces. It's an absolutely beautiful, profound symmetry. The source material really puts it perfectly. The transpose of the geometric Jacobian directly maps end effector wrenches to the required joint torques. The same matrix covers both velocity and force relationships. I mean, it's hard to overstate just how powerful and elegant that connection really is.
So, let's just recap what we've seen. Screw theory gives us a single, consistent language for talking about both motion and forces. It gives us this really powerful geometric intuition, letting us think about how robots move in a much clearer way. And maybe most profoundly, it reveals this elegant duality, this deep, fundamental connection between how a robot moves and the forces it deals with. And all of this leaves us with a final thought to chew on. As our robots and machines get more and more complex, how might these unified frameworks, like screw theory, inspire us to find simpler, more intuitive ways to design and control the next generation of all our technology?